Hello. This is the first lecture of the course on vibration and structural dynamics. In this lecture, I will mostly give an introduction to the basic idea of structural dynamics, why we need to study it, what are the different modules of the course. Though this has been said in the trailer slide, but I would also briefly discuss about this for the completeness of the course. So the course is divided into 4 modules, as I said earlier. The first is the single degree of freedom, the next is multi-degree of freedom, then we will move on to continuous system, and finally a small module on analytical methods. So in single degree of freedom, we will introduce the concept of vibration of single degree of freedom system. We will talk about what is meant by a degree of freedom. We will talk what is an equation of motion and how to derive it. Then we will study the undamped and damped vibration of single degree of freedom. Then we will solve certain examples of free vibration just to get more acquainted and comfortable with the concepts, and then we will move on to force vibration. Under force vibration, we will talk first about harmonic loading, which is a very common form of loading, then move into finding out the response for arbitrary loading using convolution integral or Duhamel integration. And finally, the module on single degree of freedom will be complete by talking about the impulse response. The next module, as I said, is the multi-degree of freedom problems. So after we complete the single degree of freedom problem, where most of the concepts will be discussed and you gain certain confidence on how to study and analyze vibration, we will move into multi-degree of freedom system. Multi-degree of freedom system, we will extend the concepts of single degree of freedom system and talk about normal mode of vibration first. Then we will find out how to figure out the natural frequencies and mode shape. Then we will talk about modal superposition principles and how to use modal superposition principle to solve the problem of multi-degree of freedom problem. Then we will move on to continuous system. Here we will talk how to analyze continuous one-dimensional continuous systems like bars and beam. We will also try to see how to find out the natural frequency and mode shape of bars and beam, and then we will go into finding out the force vibrations of bars and beam. Finally, the course will end on a module on analytical methods, which is finding out the equations of motion using the energy principles. The most common out of it is the Hamilton's principle and Euler-Lagrange equation. These are the references that we are going to follow. The main or the primary reference that I am going to follow in the course is Fundamentals of Vibration by L. Myrovich. This is published by an Indian edition by Tata McGraw-Hill. There are other variation of this book, other editions, so any of the editions is fine. Then we will also follow to certain extent the theory of vibration with application by Thomson and Dale. This is also by Pearson and an Indian edition is available. Then we will also use mechanical vibration by S.S. Rao. This book has a lot of solved example and is really helpful for the student to understand how to solve problems using the concept that has been learned in this course. So why should we study vibration? That is the fundamental question that one needs to understand and appreciate before we go into go further into the course, into knowing why should we analyze vibration, why should we spend so much of time in understanding vibration. So vibration is everywhere. I mean, wherever you look, everywhere there is vibration. Right, I am speaking, this is because the vibration, this is because the sound that is propagating, which is a form of vibration. Okay, the car that we use to travel is vibration. So this is a classical example that I am going to talk about how catastrophic the vibration can be if it is not properly understood before designing a structure. So this is a classical example which is used as in almost all vibration courses. So this is the famous Tacoma Narrows Bridge, the first Tacoma Narrows Bridge, which is in the state of Washington, USA. This was built sometime in 1940s. So, this bridge was designed considering all vibration aspects, but they didn't consider the torsional vibration of the bridge. So, on one day when there was a slight wind, not even a gust, the bridge started vibrating vigorously. Okay. You can see this GIF file which is taken from Wikipedia, where you can see that how vigorously the bridge is vibrating. Okay. The vibration is very much visible to everyone, and finally, because of this large and huge vibration, the bridge ultimately collapsed. Okay. Luckily, there was no casualty, there was no one injured in the bridge. That was a miracle, but the entire bridge completely collapsed within few fractions of second. Anyways, a new bridge was again built to replace this bridge, but this is an example which shows that how bad a vibration can go. The second example is that of Aloha Airlines. It was in again sometime in 1970s. So, this Aloha Airlines was in full flight, and the top part of the fuselage just got toned away because of some fatigue crack that was there, and which grew enormously while the flight was in full flight, and the top part of the fuselage just got torn away. So, except one flight attendant actually died in this incident, and all other passengers were again miraculously saved. So, this also shows that fatigue crack, which occurs due to the vibratory load experienced by the structure, the cyclic sinusoidal kind of load that is experienced by a structure, how catastrophic such kind of vibration or fatigue load can be. But saying all this, we should also remember that vibration can also be good. I mean, there are bad vibrations, there are good vibrations as well. We are able to hear because of the vibration of eardrums. We all know that, right? So, there are lots of devices that are built to enhance the hearing of people who has impairment in the hearing. To design those kind of devices, we need to understand very well the vibration of our eardrum and other biological organs and parts of our body. So, even to enhance the benefit of vibration in this kind of devices, one needs to understand the vibrational concepts very well. So, the music that we hear is nothing but harmonious vibration of the strings and the percussion instruments that one goes through. So, let me now get into more technical part of the course. So, I have always faced this question that what is meant by an oscillation and what is the difference between oscillation and vibration. So, let me try to first define it. Oscillation is a to and fro periodic motion about a position. Okay. Any to and fro motion about a position is called oscillation. Okay. And mechanical oscillations are called vibration. Structural dynamics has a much wider scope than vibration. So, it not only includes to and fro vibration or oscillatory motion of a particle, it also includes other form of vibration, other form of dynamics or response of the structure which changes with time. So, vibration is a subset of structural dynamics, and structural dynamics has much wider scope than vibration. So, in this course we will discuss both about vibration, both about periodic to and fro motion as well as structural dynamics, which need not be an oscillatory motion. So, before we get into vibration, we should understand certain terminologies involved in vibration, involved in the study of analysis of vibration very well. So, these are the definitions and terminologies that are going to be going to stay till the end of the course. So, we will spend some time in understanding what are meant by this terminologies and definition. So, the first terminology that one should get acquainted with is the degree of freedom. So, what is meant by degree of freedom? So, all of you all must have heard about degree of freedom. So, it is the number of independent coordinates required to describe the motion of a body completely. So, I have highlighted these two words, independent and completely. So, these two words are very important. So, a degree of freedom should be independent and the total number of degrees of freedom should completely describe the motion of a system or a structure. So, the very basic, the very fundamental form of a vibratory system is a single degree of freedom system, which has a single degree of freedom. And a classical example of single degree of freedom system is a spring mass system. So, it consists of a spring and it consists of a mass m. So, let us consider this system which has consist of a mass m and which consists of a linear spring k. So, it has an unstretched position of the spring where the spring has not undergone any displacement, and now if we move the mass or perturb the mass from this neutral position, then we shall be able to give this mass a vibratory or oscillatory motion. So, many real life structure, though this single degree of freedom system looks a very elementary form of a structure, but many real life problem can actually be very well approximated by a single degree of freedom system. The classical example is an overhead water tank. Okay, a overhead water tank can be very efficiently modeled as a single degree of freedom system, and almost everywhere a water tank can be modeled as single degree of freedom system, and all the earthquake analysis, the analysis of the response of the water tank due to wind load is performed by assuming it as a single degree of freedom system, and the results that we obtain from the analysis is very close to the real life result. The other example, practical example where a structure can well be approximated as a single degree of freedom system is that of a cable car. So, all of you all must have seen a cable car. So, a cable car can also be very well approximated by a single degree of freedom system. So, let us, the second terminology that one should get accustomed to is the equation of motion. So, what is meant by equation of motion? Okay. So, before analyzing any system, we should first understand what are the degrees of freedom of the system. The second thing that we should understand is how to derive the equation motion of the system. So, by definition, equation of motion is the mathematical expression defining the dynamic response of a structural system. So, if we are able to solve an equation of motion, then we get the complete description of the response of the structure as a function of time. So, there are various methods to derive the equation of motion of a system. The most basic and most easy to understand method is the dynamic equilibrium using D'Alembert's principle. This is the method that we will be using. This is the method that we will be using through most of the courses. Okay. The next other two techniques that are also commonly used for finding out the equation of motion of a system are the principle of virtual work and Hamilton's principle using Lagrange equation. So, these two we will talk at the later part of the course. These two also derives the equation of motion of a system, but they use energy of the system to derive the equation, unlike the first method which uses the equilibrium of forces to, or the force balance, to find out the equation of motion of a system. To find out the equation of motion of a system. So, the next job is to find out the equation of motion of a single degree of freedom system. So, let us go back to the basic spring mass system that we have talked about. So, which have a mass m, a concentrated mass, it can actually be considered as a point mass, and a linear spring with a spring constant k. A force Ft is acting on the mass. The force is a function of time and therefore can be called as a dynamic force, okay, instead of a static force which is not a function of time, it is constant throughout the time. And the response of the system, of this spring mass system, is ut, which is also a function of time. So, we have to notice two things here, that the force that we apply is a function of time and the response that we get is also a function of time. So, now what do we do? How do we understand, find out the equation of motion of the system? Okay. So, it is very similar to the equilibrium equation that you find out for a static problem. So, suppose we have a static problem where we do not have this force Ft, okay, and if there is no force Ft applied on the structure, then my response u will not have a time component and it will be constant with time. So, in that case, how do I draw the free body diagram of the system? If we want to draw the free body diagram of the system under static condition, we will take the body mass m, okay, we will apply the force Ft. There would be a spring force that is coming on the mass m, that can be written as kut. Now, when the system becomes dynamic, the only thing that you have to do is add an inertial force which is mass times the acceleration of the system. This mu double dot is the inertial force and this has been given by D'Alembert's principle. The D'Alembert's principle states that when a mass undergoes an acceleration or a motion, acceleration, there is always a force which is proportional to the acceleration, which is called the inertial force, and it acts opposite to the direction of motion of the body. So, apart from writing all the forces on the free body, we also need to add additional force which is called the inertial force, which is nothing but mass times the acceleration of the body. Okay. So, once we add the inertial force which is acting in the direction opposite, so this is the direction of the motion ut, we apply the inertial force in a direction opposite to the direction of the motion of the body. So, once we add the inertial force, once we add all the other forces that are acting on the body, our free body diagram is complete. Okay. Now, we just apply the very simple force balance and write down equate the force on the left hand side to the force acting on the right hand side, and we get this nice equation of mu double dot plus ku is equal to Ft. So, this is the equation of motion for your single degree of spring mass system. So, now when Ft is equal to 0, we will call it free vibration. When Ft is not equal to 0, we will call it as force vibration. So, in the coming lectures, we will be talking about, in the next few lectures, we will talk about free vibration for a damped and undamped system. So, let us get into few more examples to show how the free body diagram of certain problems can be derived. These examples will help you to get a grip on the concepts that you have learned in this lecture part of the course. So, first let us solve a very simple example. Let me call it as example 1. So, where I have a spring mass system, but here instead the mass being horizontal, we make the mass to be vertically suspended by a spring K. So, I have a mass M, I have again a linear spring K, but instead of it being horizontal, we make it vertical so that the gravitational force mg or the weight acts through the mass. Okay. And now let us try to derive the equation of motion of the system. Let us try to derive this. Now, the first thing that you should do whenever you have to find out the equation of a system is to draw the free body diagram. So, let us draw the free body diagram of this system. Okay. Now, before going into the free body diagram of the system, first let us observe what is going to happen to the system statically. Now, since the system is suspended vertically and a weight is acting on the system, the spring is no longer going to remain unstretched. So, suppose this is the unstretched position of the spring. So, this is the unstretched position of the spring. So, this is the unstretched position of the string. Now, because of the weight, the mass m is not going to remain in the unstretched position and it will come to a new position, which is the static equilibrium position of the mass. So, static equilibrium position, right, and let us call this displacement to be u static. Okay. Now, you can easily say that k into u static is going to be mg, right, and let us call this as our equation 1, right. This is very straightforward, that k into u static is going to be mg, because u static is the static displacement that we obtain because of the weight of the system. Now, let us note this before we go into free body diagram. Now, let us draw, and the vibration, one more point is that the vibration will now happen about this new location. Okay. So, the vibration is now going to happen about this red location, right. So, we will measure the vibration about this location. So, this is going to be the equilibrium location about which the vibration is going to happen. Okay. So, now let us draw the free body diagram. So, if this is the mass m, one force of course is going to be mg. Okay. The other force is going to be k into u plus u static, right, because already the u static is there. So, k into u static is always going to act on the mass m plus the new u, which is the vibration or the time varying displacement about this new equilibrium position shown in red. Okay. Now, these are the forces that are acting on m. Apart from this, because the vibration is happening in this direction, there has to be an inertial force which is going to be m into u double dot. Okay. This is coming from the equilibrium condition, from the D'Alembert's principle, and this is my inertial force. Now, I have to just write down the force balance equation. Let me just write down the force balance equation. So, if I write down the force balance equation, I have m u double dot, okay, that is the force in upward direction, plus k into u plus u static. Okay. U is a function of time, U static is not a function of time, and that is equal to the force acting in the downward direction, which we call as mg. Okay. Now, the interesting part is that mg, I have seen from equation 1 that mg is equal to k into U static. So, this 2 cancels out and my final equation is going to be mu double dot plus k mu double dot plus ku is equal to 0. Okay. So, this is my equation of motion. So, it is very interesting to note that in this equation of motion, we do not see the weight term or the mg term coming into picture. Okay. So, the moral of the story is that a static force, a force that is not changing with time, is not going to appear in the equation of motion. Okay. So, let us solve another example on finding out the equation of motion. So, this is an example of a pendulum, a simple pendulum, okay, which is a mass m suspended by a string of length L. So, you all know how the pendulum will vibrate. Okay. The new position of the pendulum after it starts undergoing vibration is going to make an angle theta. The length is going to remain L. Theta we assume as small. Theta is a small displacement, is a small angle. Okay. Now, how do I find out the free body equation of motion? So, now first let me draw the free body diagram. Okay. Okay. So, if I draw the free body diagram, so what are the forces that are acting on mass m? On mass m, one is the force mg, which is the weight of the body. There is a tension T that the string is giving. So, the tension T which is making an angle theta with the vertical, and then since it is undergoing a displacement in the tangential direction or in the curvature direction, we have to consider an inertial force. So, which is going to oppose the in the opposite direction of the motion, and this is going to be ml theta double dot. Why ml theta double dot? Because L theta is the translational displacement, theta is the rotational displacement, L theta is the translational displacement, and L theta double dot is the translational acceleration. So, this is my inertial force that I am adding to the system. Okay. So, this is the inertial force. Now, I have to write down the force balance in the tangential direction. So, let me write the force balance equation in tangential direction. Okay. If I do so, then what are the forces in the tangential direction? One is ml theta double dot, okay, which is in the tangential direction. Note that this tension that is there in the string is always 90 degree to the tangential direction, because the string is always 90 degree to the tangential direction. So, no component of this tension T is going to come in the tangential direction. So, the T component is not there. What else is there? This mg which is vertical is going to have a component in the tangential direction, and that component is going to be mg sin theta. Okay. And there is no force on the other side. So, mg sin theta is equal to 0, which can be written as L theta double dot plus g sin theta is equal to 0. Okay. Since we have said theta is equal to small, sin theta can always be approximated as theta, and this equation can be written as L theta double dot plus g theta is equal to 0. Okay. And this is my equation of motion for the pendulum. There are two things that I want to highlight. So, in the previous example, I have shown that the mg is not coming in the equation of motion, but here on the contrary, I have shown that mg is coming into the equation of motion. Why is this happening? Because in the previous case, mg was constant, it was not varying with time, but here the component of mg that is coming in the equation of motion is mg sin theta. So, it has a theta part which is varying with time. So, this component of the weight that is coming is varying with time, and therefore, it is coming in the equation of motion. Okay. So, this the other thing that I should mention is that here theta t is the degree of freedom that we have assumed. Okay. So, one can on the contrary think of taking the xy coordinate of this mass as the degrees of freedom, but one should note that this x and y are not independent to each other. X and y are always independent of each other. So, this is not a 2 degree of freedom, but rather a 1 degree of freedom, which is theta t or x expressed in terms of y. So, with this we will conclude the first lecture on the course. We will meet for the second lecture, where we will talk about the free vibration of a damped and undamped single degree of freedom system. Thank you.